Good morning. So it's a pleasure to have the opportunity to introduce Quandela to you this morning. So I'm Xavier Pereira, and I'm going to talk a little bit about what we do and how we can effectively accelerate the usage of quantum in Korea. So just to introduce Quandela, how many of you have heard about Quandela? Good, excellent. So first I'd like to introduce Sam Kim, who's just on the first row as our country manager for our office in Korea. This is a French company, and we obviously have done some quantum computing for many years, but the company was created in 2017. We have offices in Europe, in UK, in Germany. We're based in Korea now, as I mentioned. We are also based in Canada. And our objective over the next 5 years is really open 16 locations around the world. So we're really trying to be a true global company. We design quantum computers. You see one of the examples here on the screen that we shipped to Canada a few weeks ago, and they are photonic quantum computers. In our company, we have today more than 120 individuals. And we're doing full stack quantum computing, so you'll be able to engage with us on hardware, software, services, obviously. And we've been the first company in Europe to provide a quantum cloud services, which put our quantum computers at disposal for all our users. And we have a community today of 1,500 users, which are active on the cloud. When you think about Quandela, you really need to think about bridging the gap between AI and quantum computing. I think you'll envision quite clearly the focus on designing an architecture with logical qubits, and that's definitely one leg of activity of Quandela, but we have also another activity which is addressing the massive audience of AI developers by basically developing the PyTorch of quantum. And that's a platform, Merlin, that we released now a month ago, which is really allowing, through simulations, to connect and embed quantum processes into AI processes. And I'll give you a couple of examples just later. So we provide cloud solutions, obviously. We design and build and deliver quantum computers for data center, for private data centers, and for HPC. And we obviously design pipeline, design use case with the objective to industrialize use case and bring them to a quantum advantage. You see some examples of companies. We're working today with more than 60 companies that have been engaged with us. On effectively all type of activities, hardware at the bottom, cloud services, and obviously use cases, industrial use cases. So when you look at our roadmap in terms of hardware and software, so today we've been selling 12-qubit photonic quantum computers. Now our roadmap is about selling and delivering 24-qubit, 48 qubits, and 100 qubits, and that's going to be our focus for the next 3 years. And at the same time, we're going to deliver the first logical qubit on our platform this year with the objective, certainly after 2028, to bring all our roadmap on 50 logical qubits and 100 logical qubits to get to the volume and to the scale, which means that from a use case point of view, there are a lot of focus right now on use case and algorithm which are more on the optimization side, so in energy, in logistics, in manufacturing, and as we develop our platform, we'll open more possibilities in simulations, typically in health, in pharma. So we're scaling through this. So I would say today, quantum machine learning optimization. Tomorrow, we will add simulation after 2029. That's the focus. So I mentioned that we're designing, building, and shipping HPC-ready quantum computers. I think what's very interesting with photonic, the differentiation of photonic, the first thing is that we use light for quantum computing. Those computers work at room temperature, so you have low cryogenics. We work at 4 Kelvin, so we don't need to go to the micro Kelvin. For us, our quantum computers work with a plug on the wall at 3, and they use 3 kilowatts primarily. to work. So we think that as we progress, that's going to be 3-5 kilowatts, but not the 30 kilowatts. We have limited decoherence because the photons don't have mass. We have loss of photons, so we have an engineering challenge to resolve to make sure we're not losing photons, but we benefit from the speed because this architecture works at the nanosecond speed. Basically, we use effectively the photons as flying qubits, which are circulating in our chip to do typically boson sampling. As we progress, the flying qubits are going to basically become a combination of matter and flying qubits. So we're going to use the spin of the electron of our quantum dots to generate entangled photons and a cluster of photons at the source. So on our path is really about scaling this architecture by creating cluster of photons, cluster entangled photons, and from there create the foundation of designing logical qubits. So all those things are basically in flight right now. This is a very modular and scalable architecture because with this type of architecture, you can upgrade quite easily. So most of our clients, when they purchase a 12 qubit, they look at upgrading to 24. And basically, we provide a plug-and-play update of the modules. The computer you see here is one of the first we released in North America. This is a computer sitting in the valley of Sherbrooke in Canada. And for us, typically, a computer like this takes 9 months to build and a week to install. There's no real necessity for strong maintenance because everything is automated. So that's also a plus for the platform. Obviously, the track record is proven with a couple of clients, OVH Cloud, Exion, GenC, and we're working with the GenC to operationalize the integration with HPC centers so we can have an architecture effectively that connects CPU, GPU, and QPU. Okay. So I always get the question, what's the differentiation? You know, what's the problem we're trying to solve? I'm not here to give lessons, or I'm trying to articulate how we approach the problems here. So on one side, we see that we have matter qubits. On the other side, we have photonic qubits, and each of them has advantages and inconvenience, I would say. And so we're trying to bring those two things together so we can effectively not only resolve the challenge of room temperature, decoherence, as I mentioned in the early stage, but also be able to scale. So what we see is that a lot of time when you do photonic, you're going to be able to build your first unit modules, but when you start to scale, that's where usually the challenge comes, because the number of devices you're going to basically bring in your quantum computing solution is pretty big, you know. So in this type of industry, they have to resolve the fact that they use brute force lasers to generate the photons. And effectively, they have a challenge potentially to manufacture and connect them all together to build scalable computers. So you get usually a big building to run this type of computer. On the other side, I think you have well, something we know very well. Huh? You know, before I was with IBM also. So the supraconductor, the atoms. Those ones, I think they are effectively, they bring matter qubits. And the challenge here sometimes is also the capacity to connect multiple computers, because a lot of time we see it, the connection is going to be through the fiber. And you need to connect effectively matter qubits with fiber to be able to extend and scale your platforms. So those are the type of problems companies work on. For us, we're trying effectively to use, as I said, the photons native. So they circulate quite easily from computer to computer because this is the foundation of fiber, basically. And we're trying to bring effectively the spin and the photons together so we can scale, create the fault-tolerant architecture, and be able to manufacture them with a limited number of physical qubits to generate logical qubits, because it takes roughly 12 physical qubits to generate 1 logical qubit with our architecture. Maybe to leave you with this slide, the last slide, I wanted to bring a couple of use cases we've been engaged on. There's no client today which is in quantum advantage or full industrial deployment. Most of our clients have gone beyond the exploration, so they've mapped their use case to algorithm. They work with us, and now they are really doing the simulation to align effectively their use case to the roadmap and figure out within the next 3 years when they can go to a full deployment and effectively try to reach the quantum advantage. So for us, the kind of target is for this kind of scenario to become really mature is 2027. We think that from there, we start to have a pretty interesting situation, and I want to explain that. So when you take photonic architecture, and what we've done with AWS is we've simulated qubits with an architecture of 9,000 core, and we've been able to generate 30 photons, so 30 flying qubits. And that's a kind of threshold for us to say beyond that, it becomes really hard to simulate, because the infrastructure you're going to need in the cloud is going to be super huge, and if you double this infrastructure, you're going to add 1 or 2 qubits only. So 30 photons, we use this as a reference. We are at 1224, and we're going to go to 2448 within the next 18 months. And that's the threshold for us, effectively, to start to apply scenarios that we cannot execute effectively on classical computers. So you get a couple of examples here that I wanted to articulate. So Crédit Agricole, we do Fallen Angel. It's typically using a classical scenario. We do this quite well with classifier. Fallen Angel are about understanding the capacity of large enterprise to reimburse their credit, you know. And we couple classical classifiers with quantum classifiers to get basically better results than just on classic. Usually a few % better, which is already a kind of interesting case. So first type of benefit we can get with this platform is improve the performance of classical algorithm with the usage of a combination of classical and quantum algorithm. The second one I wanted to bring to your attention is more BMW and Airbus, where we use quantum machine learning. So this use case here is about autonomous driving. We won the challenge with Airbus and BMW to resolve an interesting case. You know, when you do autonomous driving, you build a database to train the cars to drive. And the challenge they got here was they had a lot of videos in the day, but not so many videos in the night. You know. So either you ask everybody to drive in the night, or what we did here is convert day videos into night videos. And when you use quantum, it's interesting, you resolve one of the problems, which is the hallucination. In that case, the light for the videos come from the sun in the day. They come from buildings in the night. And if you just use classical computers, you see a lot of hallucination. So combining the two really help us to improve the situation and remove a substantial number of elements of hallucination. I'll give you one last case, EDF, that I think very interesting. So we work a lot in the energy, and EDF, they're very interested. They have nuclear plant, dams, and very interested to understand the stability of their buildings. And when they do this with classical computer, the unit of volume that they use to evaluate the stability of the building is the square cube meter. When they use quantum, they can go to the milli square meter. So it's a lot of granularity that you can capture from there with a volume of data which is limited. I think the benefit of quantum is not so much using a high volume of data, but reducing the volume of data and creating more insights. And so this is now a scenario that we replicate all over the world with most of the energy companies that have, like Hydro-Québec, for example, in Canada. So we're looking for that. And what you learn there is effectively this optimization of the situation on those dam buildings. And what's interesting is you can compare, like we work also with hospital looking for how the fluids circulate around the tumors, and that's exactly the same algorithm. So interesting for us also to think about how we compare the algorithm and the use case across the different industries to develop new type of solutions. Okay, so I'm getting out of time, so I want to thank you and really remind you that through the cloud that you can access every single day, you can effectively give the opportunity to the mass to access quantum computing. That's a journey that we're pursuing all together. Thank you.